All right, friends and neighbors, welcome back to our CCNA track here. Today we are doing CCNA Chapter 9, Spanning Tree Protocol Concepts. Now, this is one of those chapters where you can read a lot about it and you can look at a lot of diagrams, but I've always maintained that spanning tree is much easier when you see it operate. So we're going to do some examples today. Now, before we get started, I wanted to give a shout out to Radia Perlman. Radia Perlman is the one who came up with spanning tree. Story goes that looping was a problem, and so she went home for the weekend, and on Saturday solved the problem, and then Sunday wrote a poem about it, which I've included on this slide. It's called Algorime. I think that I will never see a graph more lovely than a tree. A tree whose crucial property is loop-free connectivity, and that's the key part here. This is all about eliminating loops. So in this video, of course, we'll do the do you know this already questions. And then this is a network access exam topic. So there's a couple of sections, right? 2.4, 2.5, those are the ones that we're working through right now. And so we want to be able to take a look at ether channels, and then we want to be able to interpret, configure, understand, when we're all done, the various flavors of spanning tree. We want to understand port states and roles, what PortFast is. It's a feature of spanning tree, or a feature on Cisco configuration devices. And then root guard, loop guard, BPDU filters, and BPDU guard. These are all options that you can employ in your spanning tree topology. And our look ahead will be to rapid spanning tree and ether channel configurations. So this is a big topic, and I could talk for a long time on it. We're going to try and keep this to the same length as the other ones. But without further ado, let's do some do you know this already questions. Question number 1, which of the following port states are stable states used when the spanning tree protocol has completed convergence? Now, there's a couple of things here. Convergence is when the topology is all done figuring out what it is. Now, maybe to preface all of these, if you're trying to go, well, wait a minute, what's spanning tree all about? I sort of say that spanning tree is the save your butt sort of protocol. And that is to say that if you make mistakes or something goes wrong with your layer 2 topology, spanning tree is running by default and saves you. And what it tries to do is figure out what the topology should be. Okay, so it does this convergence thing. That is to say, we've got a topology that's in one state, and then it moves to the next state. That process is called convergence. And so what we want is a stable topology. So the two port states are blocking and forwarding. Those are the two end states. All the other ones are what we call transitional. Question number 2, which of the following bridge IDs wins election as root, assuming that the switches of these, or with these bridge IDs, are in the same network. So the key to all of this is that the root election is based on the lowest bridge ID. Bridge ID, and I'll say this a bunch of times, but bridge ID is a combination of priority plus MAC address. And so the one with the lowest one wins, and that was C. Question number 3, which of the following are transitory port states used only during the process of STP convergence? Choose 2. So if stable states are blocking and forwarding, the other 2 are listening and learning. Those are transition states where we don't stay on them for but a couple of seconds. Question number 4, which of the following facts determines how often a non-root bridge or switch sends an STP hello BPDU message? Well, we'll find out that there are several timers associated with spanning tree, and the hello timer is the one that controls this particular message. Question number 5, which of the following RSTP, rapid spanning tree port states, have the same name and purpose as port states in traditional STP? Choose 2. And that was the forwarding and learning states. Those are the same in those 2 versions of spanning tree. Question number 6, which of the following statements correctly describes a port role that is waiting to take over for another port role? Choose 2. These were A and D, and what we have to realize is that in this case, when a port is blocking, that doesn't mean it's dead. That might mean that it's ready to go. So if you need me, I'm here. Right now I'm blocked, but I'll be ready to change if you need me. And so that's blocked but alternate and blocked but backup. And these two become different kinds of ports when they switch. We'll talk about root and designated ports here in a little bit. Question number 7, what STP or RSTP feature causes an interface to be placed in the forwarding state as soon as the interface is physically active? And that is PortFast. PortFast moves us to forwarding really, really quick. And again, if you're confused by any of these, don't sweat it. We're going to do them all and go through the whole thing. Question number 8, which optional STP feature acts as a subset of incoming STP BPDUs to disable the port, but also allows and processes some other STP BPDUs, and that would be root guard. All right, so that's did you know this already, and an explanation a little bit of those. Let's dive into what spanning tree is all about. So first of all, loops are bad, and we're going to talk about a couple of reasons why loops are bad in Ethernet networks. The problem is that sometimes we'll build networks and we say, I know what I'll do. I'll hook up a couple of cables, extra cables for redundancy. If something goes wrong with this switch or this link, I'll have this one over here. Well, in an Ethernet network, that creates a loop, and that's bad. So spanning tree helps us out by eliminating the loops. Even if you put one in there, spanning tree will stop it from looping because, again, loops are bad. So a spanning tree eliminates the logical loops, right? It doesn't walk up to your switch and unplug the cable. What it does is disables the port from sending or receiving frames. And so that's how it breaks the loop. And what this means is that it forces the looped topology to behave more like a tree or a star wire topology, which is the way Ethernet is supposed to work. So we want to eliminate loops, but we don't want to cut off anybody, right? We don't want to create any problems for nodes that might have been on the end of a link that was blocked. So everybody is still going to have connectivity. We're not going to isolate any network segments, but we do want to eliminate those loops. So one of the things to remember is that by default, all ports are in VLAN 1. So we could easily say, well, we're talking about switches or bridges that are involved in spanning tree, but really we're talking about VLANs that are involved in spanning tree. And spoiler alert, every VLAN can have its own instance of the protocol running, which can really confuse things, but we'll work our way through it. So what we want is ports to be in the forwarding state. That means they're sending and receiving traffic. And blocked, which is another terminal state, says, I'm going to get your stuff, but I'm not going to do anything with it, and I'm not going to transmit anything. So STP is the first one, spanning tree. We call it traditional spanning tree. It was standardized a long time ago and is part of 802.1d. And rapid spanning tree said, well, spanning tree is good, but there's a lot of problems with it, so we're going to have some fixes to it. And so that's now standardized in 802.1q. There's lots of versions along the way. But we'll do more with that in the next chapter. Okay, so why do we need spanning tree? When you have a loop, it creates a couple of problems. It creates a broadcast storm. What does a switch do with broadcast, multicast, and unknown MAC address traffic? It floods it, right? What if I've got switches connected in a loop and switch 1 says, I'm going to flood this out all ports except for the one that it came in on? Well, then it sends it to other switches and they do the same thing. And so what happens is this continually circulates in that way. So let's take a look at what a broadcast storm might look like. Now this presupposes, right, we don't have spanning tree or anything else. And let's say that PC1 just wants to talk to PC2. That's all that it wants to do. And so how do we do this, right? We know that PC1 would process its host routing table and then would say, oh, PC2 is on my network, and so I can communicate with it directly, and I'm going to forward out traffic. But first, I need to find the MAC address, so I'm going to generate a broadcast frame. And the broadcast frame is an ARP request. So that might look something like this, right? So we say, I'm going to send out an ARP request. What does switch 3 do with broadcasts? they forward them out every port except for the one that they came in on. And so that means switch 3 would forward it up to switch 2, and it would also forward it to switch 4. Well, let's talk about what switch 2 would do. So switch 2 says that's a broadcast frame. I need to send that out all ports except for the one that it came in on, and it sends it down to switch 4. But in the meantime, switch 4 has also gotten this particular copy of the broadcast frame. And it says, oh, that's a broadcast frame. Let me forward that out all ports except for the one that it came in on. So it sends it up to switch 2, but also to PC2. All right, so it goes over here. Now the PC2 thing we don't really care about. Now what's going on over here, right? So switch 4 sent the broadcast frame to switch 2. And switch 2 says, oh, another broadcast frame, good gracious me, what should I do? I'll send that to switch 3. And switch 4 got the one from switch 2, right? And it sent it to PC2, but it also sends it across to switch 3. So what happened? PC1 sent out one ARP request, broadcast frame, and switch 3 sent it to switch 2 and switch 4. Both of these copies went around the loop, and then switch 3 ends up receiving a copy of its own transmitted broadcast frame. This is the danger of a loop, and this is a broadcast storm. What would switch 3 do now? Well, it would send it right back to switch 4 and switch 2, but going in the opposite direction, and send it to PC1. This single broadcast frame could bring this network to its knees. So that was broadcast storm. MAC table instability. What this means is that the switches believe that a MAC address exists on one port and then switches to another port. So this is also called address flap sometimes. It's called address flip-flopping. But the switches would have really no idea at any particular time where the MAC address was, because it would appear over there, it would appear over there, and so on and so forth. Well, what does that look like? From the perspective of switch 3, when this first happened, switch 3 would think that PC1 is right there. And if we follow the broadcast that goes along to switch 4 would believe that PC1 is right there, right? PC2 or switch 2 would believe that PC1 was right here. Well, now the broadcast frame continues along, but now all of a sudden, switch 2 believes that PC1 exists right here because it's the same broadcast. Switch 2 would forward the same broadcast frame down to switch 4, and switch 4 would believe that PC1 exists right there. But it gets better. This goes across to switch 3 and down from switch 2 to switch 3, depending on the timing of the messages, right? Switch 3 would believe that PC1 is on the upper port, and then it might believe that it is on the port connected to switch 4. So where does this MAC address really live? MAC address table or source address table instability. And the third thing that the book talks about, why we need spanning tree, is that we got multiple copies of the frames, and we saw that with the broadcast storm. So which frame are you supposed to answer, right? We got all these ARP requests that are out there. Did I answer? Did I not answer? Do I answer all of them, right? So it's just all of this confusion out on the network. Okay, so spanning tree blocks ports, eliminates these loops, and eliminates or prevents all of these problems. But how does it do that? And the answer is that spanning tree is a protocol that's running on all the switches. And they exchange special messages called BPDUs, Bridge Protocol Data Units. And then we run a comparison algorithm to help us figure out what to do based on the information that's contained in a BPDU. So, what does a BPDU look like? Here is a frame that is the special multicast Ethernet frame that is a BPDU. So we can see up top, we've got this multicast destination. This multicast destination is reserved for spanning tree. So switches pay attention to it, but most other nodes don't. And here is the operating part of the BPDU, all of this stuff here. So down at the bottom, we've got timers. We'll talk about those later, but really, this central part here, the comparison fields, are the ones that we really care about. Those are the ones that we're going to act on. Those are the ones that are going to have the information that will really describe how we are supposed to do things. Now, this is just a slide. What does it look like in Wireshark? If I was just capturing from a switch, right, I would see that all of these spanning tree messages come from my switch. And this is just, I made a screenshot out of this, right? This is the 802.3 frame. It's 802.3 because the length is less than 1500 or 1501. And then we've got logical link control, which is spanning tree, and then all of the stuff in the BPDU. All right, operationally, how does it work? Well, step one is to elect a root, switch, or bridge. Now, back in the day, there were no switches. There were bridges. And so I will use switch and bridge interchangeably. Today we talk about switches. And the book also uses switches and bridges interchangeably. Now, to begin with, I've got this topology at the top, right above me here. And this shows a very, very small switch topology. And what we have to realize is that spanning tree is on by default. So the minute I am doing anything with my topology, the minute I connect these together, the switches are exchanging information. So let's get used to a couple of labels. We've got root switches, we have designated switches. We have designated ports, and we have root ports. And then we've got the operational stuff that we have to worry about. Now, to elect a root, what we want is the lowest bridge ID. Now, the bridge ID is a combination of the bridge priority plus the bridge MAC address. To start off this process, everybody believes that they're the root. And then we have to sort that out. And we sort that out by exchanging the BPDUs. So they exchange hello BPDUs, and other switches compare their bridge IDs to the one received. The lowest bridge ID, that is the lowest combination of the priority plus the MAC address, wins. Then that bridge ID becomes the root ID. Now, by default, the bridge priority is 32,768. If you convert that to hexadecimal, it's 8,000. But on Cisco devices, we add the VLAN ID. By default, the VLANs are in VLAN 1, and so that makes it 32,769 or 8,001 in hexadecimal. Now, this is just an example down here. Let's see what the operating topology looks like. So here we are in the first of our two topologies that we're going to look at today. And what I've done is added the MAC addresses of the switch. Yes, switches have MAC addresses. Every port on a switch has a MAC address, and the switch itself has a MAC address. Now, these are the two MAC addresses, but we just got done saying that bridge ID is a combination of the bridge priority plus the bridge MAC address. So I'm going to show you something that is not in the text for this chapter, but I think it's really, really helpful. And this is the show spanning tree command. And right here is the information for this particular bridge, right? So this is where I got the MAC address, and there's the priority. Now, I'm going to convert the priority to hexadecimal. So I'm going to say 8,001, right, like this. So there is this switch's priority, and I'm going to do the same thing over here, 8,001. Now, how would we figure out which switch should be the root? Well, we go by the MAC address and the priority, but the priorities are the same. So if the priorities are equal, we just keep going and we try to find the lowest number. So 0002, 00E0. Oh, 0002 is lower. So this switch automatically becomes the root. And so if I look at the information given to me here, I can see my bridge ID, right? Combination of those two. And I can also see the root bridge ID right here. And that is why switch 1 believes that switch 0 should be the root. Now, if we look at the same information on switch 0, it says this bridge is the root. And take a look at the root ID and compare that to this bridge's ID. They're the same. So when a switch has the lowest bridge ID, that also becomes the root ID. And then we can see some details about a port. So port 24 has a designated role. Its status or its state is forwarding. We can see it's got a cost associated with it. And the port has a port ID, which is a combination of the port priority plus the port number. If we look at our other switch, it has two ports that are active. So port 1 and port 23, they're both forwarding. One is designated and one is the root. They both have a port cost of 19, and here are their port IDs. The 128 base priority, or 80 in hex, plus their port number. Let's do one more thing while we're here. Let's take a look at the simulation. And what I care about is what's going on this topology, so I'm going to sort of cover up the other one. There we go. So the root switch sends out a BPDU, and then shortly after that, this switch, which is a designated switch because it's got the shortest path cost to the root, right? We're gonna do these terms a lot. So let's take a look at what a BPDU looks like. We can see there's that multicast address, and then here in the center, we see our root ID. We see the root path cost is 0. We see the transmit bridge ID. In this case, it happens to be the same because we caught this one from the root. And there's the port ID. This is the conversion from hexadecimal. Well, what does one look like if we catch it downstream a little bit? Again, the multicast destination address. But here the root ID is the root switch, understandably, but the path cost went up because we're farther away from the root. We have a different transmit bridge ID because it came from a different switch, right? It's downstream from the root. And the port ID also changed because this is coming from a different port on a different switch. Now, sometimes that's a little confusing because the different switches have the same port numbers and therefore the same port ID. What we have to really pay attention to is which switch this came from. So hopefully at this point we understand the root election process. Step 2. Let's figure out our ports and our bridges. What are the other names? What are the states? What are their roles? So let's remember that ports also have an ID, which is a combination of the port priority plus the port number. We saw that. The default is 128 or 80 in hex plus whatever the port number is. So ports have a role. A port is either going to be a root port or a designated port. Root ports have the least cost to the root switch. They're the closest to the root switch. Another way to think about this is they point the way to the root bridge. Designated ports are non-root ports. So anybody else that's forwarding but not a root port is going to be a designated port. In other words, traffic passes into these ports on their way to the root. Now, ports go through different states as the topology converges. The states, and we just sort of have to listen to this, all ports come up blocking. That's really important to remember. That's so that we don't accidentally forward into a loop. And then they try to figure out the topology. So they listen, and it turns out they listen for 15 seconds. Then they learn, they're calculating the topology, and they do that for 15 seconds. And then they either go to forwarding or blocked. Disabled is another port state, but it doesn't have anything to do with spanning tree. Remember that the bridge with the lowest bridge ID becomes the root, and the bridge or switch with the lowest cost, the lowest path cost to the root, is called a designated bridge. So in our topology above me here, we figured out what the root is. Well, now we know what the designated ports are. The designated ports are traffic flowing into the switch on the way to the root. All ports on the root bridge or switch will be designated. We have these root ports right here in RP. That is the port that has the lowest cost to the root or points the way to the root. And then we've got another designated port. The port roles become important to us because in a converged topology, if something happens, the ports can change their role or what they're doing in a particular topology. Step 3, if we have a loop, which is the other topology we're going to work with, what port do we block? So a good question to start off with is, how do you know that there's a loop? And you know that there's a loop because you hear BPDUs advertised, but on different ports. And you go, wait a minute, I heard about that route over there, and then I heard about it again over here. There must be some loop in the topology. So that at that point, you have to sort of act on it. And what we're going to do is we are going to use the comparison algorithm to compare those 4 fields that I showed you that are in the BPDU, right? The root ID, the path cost, the transmit bridge ID, and the transmit port ID. Depending on the topology, we'll use those fields at different times to break the loop. Cost is how far away you are from the root, but it's based on the speed of the port. Okay, so it is the sum of the costs associated with an exit port to the root. All cost coming from the root, right? So all the BPDUs coming from the root will have a cost of 0. And then everything else depends on where you are in the topology, but it's additive. So if you have a port that's going to the root and it's a gig port, then the cost is 4. 10 gig is 2. If it's fast Ethernet, then it's 19. And if it's 10 megabits, then the cost is 100. So when we figure out which port to block, first up we say, all right, who's got the lowest cost? The other port should block then. If the cost is the same, who's got the lowest bridge ID? If the cost and the bridge ID are the same, who has the lowest port ID? Okay, that was a lot. Let's do some examples. So we're going to focus on our 3-bridge topology or our 3-switch topology. And I've got the MAC addresses up there again, but we know, of course, that each one of these is prefaced by the priority. And by default, the priorities are all the same. Now, this topology is already converged, but we're going to break it. But before we do, let's figure out, based on the priorities and the MAC addresses, which switch would be the root. Well, if we take a look at the priorities, they're all the same. Up here, the MAC address begins with 00D0, 00D0. Oh, they're the same. That's a tie. Oh, wait a minute. This one over here is 0001. So based on that, we would say that switch 3 in this topology would be the root. So that's my guess. Let's see if we can verify that. So I'm just going to do a show span again. And this bridge is the root. So the transmit bridge ID, right, and the root ID are the same. So that worked out. But we can see that this port here has got this amber circle or orange circle. So that means that it's not doing anything. Well, what does that look like if we take a look at switch 4? And we can see that port 23 is an alternate port and it's blocked. So it's not designated, it's not root, it's not forwarding traffic here, it is blocked. Let's see if we can figure out why. If I take a look at the costs coming from each switch, this helps us understand what's going on here. So if I take a look at the BPDUs that are going in this direction and the BPDU that is going in this direction, what I should see is that the path cost is 0. So I'm going to make a note here. Path cost equals 0. And path cost equals 0. BPDUs flow away from the root. So now let's do our simulation. We're going to run this. And right there we see things coming from switch 3. The one going to switch 4 has a root path cost of 0. All right, so that checks out. The one going to switch 2 has a root path cost of 0. So we now know that our understanding is okay so far. Let's see what happens next. So switch 2 sends a BPDU to switch 4. What would the path cost be here? Well, the path cost is 19 because on the way to the root, the transmit cost of a fast Ethernet port is 19. Now, there will be no BPDU that goes from switch 4 to switch 2, but we could make a note and we could say that the cost going this way equals 19. But now the question is, why did we block this port? Well, if we pretend that switch 4 would have sent a message to switch 2, what would the path cost have been? It would also have been 19 for the exact same reason, right? This transmit cost right here would be 19. So in the BPDUs that we would be comparing, we would say, what's your root ID? Well, the root IDs would be the same. They would be the ID of switch 3. Ah, what would be your path cost? My path cost is 19. What's your path cost? Oh, my path cost is 19. So they're the same. So now it comes down to the third field. And the third field would be the transmit bridge ID. Which one of these two switches has a better transmit bridge ID? Well, the priorities are the same. The first 2 bytes of the MAC address are the same, but then we get D3B9 FF79. Oh no, switch 4 loses. It's higher. So switch 2 has a better bridge ID, which means that switch 4 has to block its port. And that's why the port is blocked on switch 4. Well, let's do one more example. We're going to go back to, let's take a look at our first topology. If I was to do something crazy like connect these two switches together, spanning tree says, wait a minute, something's afoot here. What's going on? If I take a look at my port states, now I've slowed this down because I'm running simulation, because we want to see the port states. So I can see right here that port 21, I changed over, I switched real quick to get it from the beginning, but we can see right now that I'm listening, right? I'm in listen state. It's listening for BPDUs. So we'll let this run for a couple of seconds. Now we need to get to about 15 seconds or so. That'll about do it. So now what I'm going to do is let's check our ports again. And now it is transitioned to the learning state. So port 21 is said, okay, I've gathered some BPDU information. I have figured out, I think, what the topology is. Let me see what I'm going to do about this. And we'll go back to real time now. What is our topology now? Or what is the status of the ports now? And we can see that on the root switch, they are both designated and they are both forwarding. What about switch 1? We've got a blocked port again. Port 22 is blocked in this case. And now our question is, why did we block port 22? Well, we have to imagine that there are BPDUs going down both of these ports, right, towards switch 1. And if we were going to compare the BPDUs, right, because this is how we decide, we would first look at the root ID. Oh, they're the same. They're both coming from switch 0. Okay, what's the path cost? The path cost would also be 0 from both ports. Okay, what's the transmit bridge ID? Aha, the transmit bridge ID. Oh, it's the same, because, again, they both came from switch 0. All right, fine. What's the last comparison field? It's the port ID. And in this case, the ports make a big difference. So this is port 22, and this is port 21. So if I was to compare the port IDs, I would say, well, it's 128 and port 21, I think, on the bottom side, which converts to 80 plus the port number. Now, if you were looking at packets, then this would all be in hexadecimal, but I'm gonna keep it pretty easy here for right now. So up top here, we would have 128 and 22, which would convert to 80, plus the hexadecimal representation of 22. The transmit port ID would be 8021 coming this way and 8022 coming this way. And so the receiving port that has the higher port ID would lose. That's why we block this particular port down here. So hopefully we have a good handle on a couple things. How we elect a route bridges versus designated bridges, port roles, designated and route, port states, listening, learning, forwarding, and blocking, and then how do we decide how to eliminate the loop, what port to block. And we do that with the comparison algorithm, route ID, route path cost, transmit bridge ID, transmit port ID. So here are some STP notes. 802.1d or traditional spanning tree is really slow, particularly in certain situations. It can take up to nearly a minute to figure stuff out. So it's quick to detect loops, but slower in other cases where the topology needs to recover. So rapid spanning tree, 802.1q, addresses many of the problems associated with traditional spanning tree. Now, during normal operations, we just see hello BPDUs, right? That's what we looked at. But if something occurs, if there's a problem or a change, then we go through what we call a topology change. That's when we'll see ports, flop roles, and everything else. Now you can change the route. In these examples, all of the bridges or switches had the same base priority, 8001. But we can change that and we can decide who we want the route to be. And sometimes that's really, really important because if I just hook up a bunch of switches, spanning tree will figure it out based on what it thinks is right. This is often suboptimal. So it's very common to change the priority of a switch. There are some timers. You saw when I was running the simulation, the BPDUs or the spanning tree messages spit out at a particular rate. That's based on the hello timer. The max age, this is what we use to determine if something's got to be changed. If I don't hear from you, right, if I don't hear from you for 10 hello times, then I think something's gone wrong and it's time to do a topology change. It's time to figure out all the paths again. The time that we go from one state to another is the forwarding delay timer. So that's why it was listening for 15 seconds, learning for 15 seconds, and then we go to forwarding. All of these times are broadcast in the BPDUs. And so the fields above me here are right out of a BPDU packet. Now, when ports are changing, the MAC address entries for that port are wiped out. We clean those out. Now, there are some similarities between traditional spanning tree and the faster rapid spanning tree. So how you figure out who the route is, how you do route and designated ports, those are the same. You block ports for the exact same reason, but instead of blocking ports, we have discarding ports. Now, things that are different are all the things that rapid spanning tree does to speed up the process, right? You can replace a route port without waiting as long. You can sometimes replace a designated port without waiting as long. and all of the wait timers are all lower. Now, in rapid spanning tree, and by default on Cisco devices, block ports are not just blocked. They're either an alternate or a backup, and you saw that when I was looking at the port roles for some of the switches. Now, you can create something called a port group or an ether channel, and this is where you bond 8 links together, or up to 8 links together, so that they can forward more traffic between devices. But by default, spanning tree would block all of the ports except one of them. But when you make them part of an ether channel, then spanning tree will not block them. And so they act together. Now, the nice thing is that spanning tree doesn't try to fix a broken topology until all of those links are down. So you're not really dependent on just one link. We still have to remember, though, that this is in between switches, and that if a switch goes away, right, you still have the same problem. Now, PortFast bypasses the whole listening and learning thing, right? That takes 30 seconds altogether. And so it is a way to speed up the time that it takes for a port to go forwarding if you know that it's just a node. That's really, really important. We don't ever do this between switches. We do this when we are connecting to a node. And I'll actually show you that here in a second. So it's only for end nodes. It's very, very handy for things like servers or voice over IP phones, because voice over IP phones try to get a lot done real quick. RSTP calls those edge ports. In between switches, we call those point-to-point links. Let's take a real quick look at that. Now, what I'm going to do is I'm going to add a couple of nodes to a switch here. So we'll just do this, and I'm going to connect them, but I'm going to configure one of them as spanning tree PortFast. So we'll do that. So I'm going to go into port 1, and I'm going to say spanning tree PortFast. Okay. Now, a lot of times the switch will say warning, right? Only do this when you're connected to a host. And that's because we don't want to create looping problems. All right, so port 1 is PortFast. And all the other ports are not. So what I'm going to do is connect this one to port 2. And we can see we've got this orange ball. So what is going on here? The port is going through listening and learning. It'll take 30 seconds to do that. But in the meantime, I'm going to connect this other PC to port 1 where I've configured PortFast. Oh my goodness, look at that. It's up already. So it bypasses the spanning tree listening and learning entirely. Now let's take a look at this topology over here. We know that this was the root, but what if I said, well, I want a different switch to be a root? Then what I could do is change the priority of one of the other switches. Now I'm in switch 4. Switch 4 is downstream of the root previously, and it has the blocked port. So what I'm going to do is change the priority for VLAN 1 because that's what we're talking about. And I'm going to say, I'm just going to pick a number, right? So what my priority is going to be, as long as it's less than 32,768, then I'm in good shape. So I'm going to change this to 4096. Now that's the base. It'll be 4097. And watch what happens on my topology. We can see that I had some instantaneous action going on here. And we can even watch to see when it converges, right? So I've made a change. So now the topology is trying to converge again, and it's trying to figure out what the topology should be. And we're exchanging BPDUs. Take a look over here. Now this port blocked. If I do a show span, we're still in listening, right? This is going to take a little while. Learning. So another 15 seconds. So we'll just let this go. So the BPDUs are now going in the opposite direction. They're starting to flow in the opposite direction, and we have a different route. So let's take a look at what's going on now. Here's this bridge ID and the priority. Take a look at the route. So now switch 4 became the route, not because it had the lowest MAC address, but because it had the lowest priority. And all of its ports are now forwarding, and now we've got a blocked port over here. Why did it block the port? Well, the route ID is over here. Path cost is 0 on these two legs now. Path cost would be 19 for both of these, but who has the lower MAC address, the lower bridge ID? Well, switch 3 wins over switch 2, and so that's why switch 2 had to block. Here are a couple of other optional STP features, right? We have BPDU guard. It disables a port if it receives a BPDU. So and actually there's a couple of these that are similar. So if I configured something for PortFast, but I also turned on BPDU guard would kill that port off if it received a BPDU. It's sort of a protection thing. Now BPDU filters, its base operation is to ignore spanning tree. So if you don't want to use spanning tree on a port, you can turn on filter. But if you had PortFast configured there, it would restore the STP logic if you received a BPDU. Route guards, I already mentioned that spanning tree will figure things out for you, but a lot of times it's suboptimal. So if you decided who the route was going to be by changing the priority, and then something happened to where there was a change in the priority of one of the other suboptimal bridges or switches, route guard would prevent that from changing your topology. Now loop guard, the example in the book is if you have a fiber link that only works in one direction. So if you've got a link that only works in one direction, you wouldn't want a port to change roles so that it was trying to forward traffic because it wouldn't work on that link. So loop guard will prevent you from changing a role. So our chapter 10 look ahead, it is more spanning tree. So you could say, oh my God, why are we doing this 2 weeks in a row? But it's a closer look at rapid spanning tree and per VLAN spanning tree plus. Now the thing that I'll point out here in the look ahead is that we'll remind ourselves about the basics, but what if we do implement more than one VLAN? Then things get really, really dicey. It gets really, really interesting. And then what if I wanted to look at additional system output? Plus, we haven't really looked very hard at some of the advanced features. All we did today was PortFast and priority. So there's a lot more to this. And I'll remind you that when you are building really, really big, bad topologies, you want high performance. You want to understand what's going on. And imagine that you're depending on failover or convergence with rapid spanning tree. You really want to understand how that works. So this has been Spanning Tree Concepts, Chapter 9. Why do we need spanning tree and what does it do, right? We talked about that, so it's pretty important. It saves us from our own mistakes and for problems in the network. We also talked about the comparison algorithm. How do we decide who is the route? How do we decide who is going to block? Port states and rules, and then all of the phases. And then we went over what's in a BPDU and how we can change things. Well, like and subscribe for more complex topology, and whether you're waiting for traditional spanning tree to fail over or the more rapid spanning tree or per VLAN spanning tree plus, may those packets always reach their destinations. I know this was a lot this time, but it's just CCNA certification. You can do this.